Welcome back to Cancer as a Metabolic Disease Basics. If oxygen stopped reaching your cells right now, what would happen? Most people assume energy production would instantly just shut down, but it doesn't. Cells have a backup system, a fast, oxygen independent way to keep producing ATP or cellular energy temporarily. And it makes sense to have a backup generator for emergencies. This backup system is called anaerobic glycolysis or anaerobic metabolism, and it is essential for us to understand this before we talk about what happens in cancer. So let's break it down. So, as I said in the intro, this is going to be about anaerobic metabolism, and this process will directly relate to cancer metabolism and will really bridge the gap in our understanding of cancer metabolism and why it's so different. So, I'm going to start out with the Stat Pearls Biochemistry Anaerobic Glycolysis publication. And it says here that through a process of glycolysis, one molecule of glucose breaks down to form two molecules of pyruvate. Depending on the microcellular environment, specifically oxygen availability, energy demand, and the presence or absence of mitochondria, pyruvate has several separate fates. In mitochondrial containing cells, or mitochondrial functioning cells, pyruvate can enter the citric acid cycle within the mitochondrial matrix and undergo oxidative phosphorylation. Aptly named due to its dependence on oxygen as a final electron acceptor, oxidative phosphorylation cannot take place in the absence of oxygen. Moreover, as the enzymes of both the citric acid cycle and the electron transport chain are within the mitochondria, cells lacking mitochondria or due to mitochondrial damage or hypoxia cannot rely on oxidative phosphorylation for energy production. And we'll talk about the TCA cycle very quickly. We'll talk about oxidative phosphorylation from a very high level. But before that, let's talk about anaerobic metabolism. In erythrocytes and oxygen-deprived tissues, pyruvate remains within the cytoplasm and converts to lactate, a process referred to as anaerobic glycolysis or fermentation. This final reaction allows for the regeneration of NAD, a cofactor that must be available in high enough cellular concentrations for the earlier reactions of glycolysis to remain favorable. Compared to oxidative phosphorylation, however, anaerobic glycolysis is significantly less efficient, providing a net production of only 2 ATP per glucose molecule versus 32 per glucose molecule during oxidative phosphorylation. Function. The anaerobic glycolysis serves as a means of energy production in cells that cannot produce adequate energy through oxidative phosphorylation. In poorly oxygenated tissue, glycolysis produces 2 ATP by shunting pyruvate away from mitochondria and through the lactate dehydrogenase reaction, LDH. In rapidly contracting skeletal muscle cells with energy demands exceeding what can be produced by oxidative phosphorylation alone, anaerobic glycolysis or anaerobic metabolism allows for the more rapid production of ATP. This is where anaerobic metabolism shines. It's not as efficient as OXPHOS, but it makes it much faster. Glycolysis is approximately 100 times faster than oxidative phosphorylation. In cells lacking mitochondria altogether, pyruvate cannot undergo oxidative phosphorylation regardless of oxygen levels. Mature erythrocytes or red blood cells do not contain mitochondria and thus rely exclusively on anaerobic glycolysis for ATP production. Other tissues such as the cornea and the lens of the eye and inner medulla of the kidney are poorly vascularized and rely heavily on anaerobic glycolysis despite the presence of mitochondria. So this is a schematic or a paper that is going to be talking about what percent of energy comes from what, depending on conditions in the body. So this paper was titled Skeletal Muscle Energy Metabolism During Exercise, and it was published in September of 2020. And it says here, the continual supply of ATP or energy to fundamental cellular processes that underpin skeletal muscle contraction during exercise is essential for sports performance in events lasting seconds to several hours. Because the muscle stores of ATP are small, metabolic pathways must be activated to maintain the required rates of ATP resynthesis. These pathways include phosphocreatinine and muscle glycogen breakdown, thus enabling substrate level phosphorylation. Keep that little phrase in your mind, substrate level phosphorylation. We're going to talk about it a lot during cancer metabolism. Anaerobic and oxidative phosphorylation by using reducing equivalents from carbohydrate and fat metabolism, aerobic. The Relative contributions of these metabolic pathways is primarily determined on the intensity and duration of exercise. For most events at the Olympics, carbohydrate is the primary fuel for anaerobic metabolism. Here, we provide an overview of exercise metabolism and key regulatory mechanisms ensuring that ATP resynthesis is closely matched to the ATP demand of exercise. We summarize various interventions that target muscle metabolism for ergogenic benefits in athletic events. So basically what this graph is showing is that depending on the intensity depends on where the energy comes from. So we see here we have glucose, which is this dark green. We have fatty acids, which is this kind of like darker but still lighter than this dark green. We have a very light green here, which is muscle triglycerides. And then we have muscle glycogen, which is the lightest of the greens. So we see here that with increasing intensity, more glucose is utilized and much more glycogen, stored glucose, is utilized. Why is that? Because as intensity increases, the amount of energy needed is far surpassing what can be done from oxidative phosphorylation in mitochondria. So therefore, this anaerobic metabolism is ramping up. So let's take a look at this from a graphical perspective. So this is a non-tumor oxidative cell. So we have glycolysis, we've talked about that. And this is the process of where glucose is broken down into pyruvate. Under aerobic conditions, the vast majority of our energy is made through this oxidative phosphorylation system in the mitochondria, if mitochondria are present or functional. However, under low oxygen conditions, where you basically are outworking how much oxygen is present to make energy through aerobic conditions, that's when anaerobic conditions will take over. And this is cytosolic substrate level phosphorylation under conditions where the body needs to make energy as a backup energy system to keep the cells alive and to keep energy moving. This is anaerobic metabolism. When I was doing the background research for this paper, I realized there are a lot of new understandings about anaerobic metabolism that have been discovered in just the last couple of years. And we're going to go over those quickly. So this paper was published in March of 2022. It's titled Lactate Contemporary Biology, A Phoenix Has Risen. Very dramatic. And it says here, after a century, it's time to turn the page on understanding of lactate metabolism and appreciate that lactate shuttling is an important component of intermediary metabolism in vivo. Cell to cell and intracellular lactate shuttles fulfill purposes of energy substrate production and distribution, as well as cell signaling under fully aerobic conditions. Recognition of lactate shuttling first came in studies of physical exercise, where the roles of driver, producer, and recipient consumer cells and tissues were obvious. Moreover, the presence of lactate shuttling as part of postprandial glucose disposal and satiety signaling has been recognized. Mitochondrial respiration creates the physiological sink for lactate disposal in vivo. Repeated lactate exposure from regular exercise results in adaptive processes such as mitochondrial biogenesis and other healthy circulatory and neurological characteristics such as improved physical work capacity, metabolic flexibility, learning, and memory. The importance of lactate and lactate shuttling in healthful living is further emphasized when lactate signaling and shuttling are dysregulated, as occurs in particular illnesses and injuries. Like a phoenix, lactate has risen to major importance in 21st century biology. And basically, what was believed was that lactate was only being produced when oxygen was low, or what has been found out in later years is that lactate is always being produced on a low level. It's just that it's mostly produced under low oxygen conditions. And that's what this paper is going to talk about in subsequent papers. So there's a crossover that is not so black and white. There's a crossover now. And what it says here, the story of lactate and its role in physiology and medicine may be a century old, but has changed dramatically in the last 3 decades. No longer conceived as a dead-end metabolite, a fatigue agent, or metabolic poison, in contemporary physiology, lactate is seen as a major metabolic intermediate that has wide-ranging impacts on energy, substrate utilization, cell signaling, and adaptation. Simply, lactate is at the fulcrum of metabolic integration. Now, rather than regarded as an oddity of exercise metabolism, the presence of lactate shuttling is recognized in fields as diverse as wound healing, cancer biology, insulin secretion, management of sepsis, learning and memory, and the treatment of traumatic brain injury, TBI. Hence, in contemporary biology, the role of lactate in metabolism needs to be understood and viewed as a phoenix risen, in contrast to the remnant of 1988 early 20th century biology. As scholars we have our limitations, and as a consequence, informal education rely on tradition to a certain extent, despite obvious evidence to the contrary. I pulled this out of this paper because this could not be more true. We rely on the traditions and what is commonly understood in science, and we don't allow that to pique our curiosity and change our beliefs, even when the evidence is contrary. And I think that couldn't be more true in cancer, where truly cancer, it's not that there aren't genetic abnormalities in cancer that are at play. It's just that cancer is clearly not a primarily genetic disease, and it is probably likely a mitochondrial metabolic disease, and that evidence is very clear, and the story has been being played out for more than 100 years, starting with Warburg. And so here we are, more than 100 years later, worried about genes when it's clearly not the problem. I thought this was really nicely put and really a nice piece of text for our upcoming discussion about cancer. Commencing with work of the early 20th century Nobel Prize winners, Hill and Meyerhoff, the role of lactate in metabolism has been misunderstood and perpetuated. Even as their cell and tissue cultures incubated in air often turn acidic overnight, textbook authors, Ledinger, that was the author of my biochemistry book when I went through biochemistry in undergrad, perpetuated the myth of oxygen-limited metabolism, giving rise to lactate formation, despite the fact that the partial pressure of oxygen in air over their mitochondrial preparations and culture dishes was 3 to 5 times higher than in vivo. Hence, a reckoning of minds and biology is necessary to understand human and mammalian physiology and metabolism in a contemporary context. Couldn't be more in agreement of that. It says later that lactate shuttling as a basis for lactate threshold in physical exercise. It has been half a century since the introduction of the concept of oxygen-limited metabolism producing an anaerobic threshold, AT, that is O2-limited metabolism during exercise of a particular intensity. The subject has been reviewed with 1541 citations of the paper of Wasserman and McElroy from 1964, is the 8th most cited paper of all time in the Journal of Applied Physiology. As recited in the recent review, in a letter from Carlman Wasserman to this author, the concept of an anaerobic threshold, based on the assumption that failure of the heart to transport oxygen adequately would result in lactic acidosis, an event that would trigger ventilatory compensations. Subsequent concepts of anaerobic, lactate, ventilatory, other related thresholds are pervasive in the literature and have represented key concepts of basic and applied physiology, sports, and pulmonary medicine. These thresholds are determined by turn points in the rise of blood lactate concentration, pulmonary minute ventilation, and heart rate during graded exercise. In a PubMed search on 20 October 2020, the term anaerobic threshold elicited 5,902 citations. In their review, Poole et al. Explained that while the basic tenet of anaerobic threshold oxygen-limited metabolism exercise is no longer acceptable, use of gas exchange threshold in graded exercise possesses significant importance for cardiopulmonary and other evaluations in patients. It later says that lactate and pyruvate as inhibitors of mitochondrial beta oxidation. I pulled this specifically because it's going to set up important concepts later on when we talk about mitochondrial dysfunction, where energy comes from in cancer, etc. When glycolysis accelerated during muscle contraction, lactate and pyruvate concentrations rise and increase the LP ratios, reducing cytosolic redox. At rest, LP ratio in muscle and venous effluent from a muscle bed approximates 10. So it means there's 10 lactates to every pyruvate under normal conditions. But if you do moderate exercise, it can go up to even 30 times more than that. By mass action of monocarboxylate pair floods in the mitochondrial reticulum, giving rise to acetyl-CoA and therefore malonyl-CoA formation, the rise of malonyl-CoA inhibits the entry of activated free fatty acids into mitochondrial matrix by inhibiting carnitine palmitoyltransferase 1. Let me break this down for a second, why it's important. So basically what they're saying is that at rest, there's some degree of lactate made. But if you exercise even a moderate intensity, it'll go up 30-fold. So you're using a lot more anaerobic metabolism at that point. What they found is that when lactate is elevated like that, it will basically shut down the ability for free fatty acids to enter the mitochondria because it shuts down an enzyme that transfers fat into the mitochondria called this carnitine palmitoyltransferase 1 or CPT CPT1. That's what it's saying. As well, the effect of glycolysis driving the accumulation of acetyl-CoA downregulates beta-ketothiolase, a terminal and rate-limiting enzyme of mitochondrial beta oxidation pathway. Hence, by mass action, allosteric binding, and its effects on cell redox, lactate acts to prevent entry of activated fatty acids into the matrix of mitochondrial reticulum, thus limiting beta oxidation of fatty acid derivatives. This is critical because, as we'll see in coming videos, when we're talking about aerobic metabolism or the Warburg metabolism, Warburg effect, what Dr. Seyfried calls cytosolic substrate level phosphorylation. Basically, when you have elevations in lactate that are 30 times higher than normal cells, that by itself, whether the mitochondria are healthy or not, that will by itself shut down fatty acid oxidation in all cells, including cancer cells, and will lead for fat not being able to be used by mitochondria in any cell. And that's important for us to understand for cancer metabolism in the future. Next paper. This is going to show how crazy adaptable our body is and how powerful this system or this backup generator of energy is for our system. So this paper was titled Lactate as a Fulcrum of Metabolism, published in August of 2020. And it says, mistakenly thought to be a consequence of oxygen lack in skeletal muscle, we now know that the L enantiomer of lactate anion is formed under fully aerobic conditions and utilized continuously in diverse cells, tissues, organs at a whole body level. By shuttling between producer, driver, and consumer recipient, cell lactate fulfills at least three purposes. Number one, a major energy source for mitochondrial respiration. Two, a major gluconeogenic precursor. And three, a signaling molecule. Working by mass action, cell redox regulation, allosteric binding, and reprogramming of chromatin by lactylation of lysine residues and histones, lactate has major influences on energy substrate partitioning. This is where it gets less technical and more interesting. The physiological range of tissues of lactate is 0.5 to 20 millimoles. And the cellular lactate to pyruvate ratio can range from 10. Remember how we talked about it, 10? That's like the resting lactate to pyruvate ratio. So there's always a little bit of lactate being made. But then if under stress conditions like extreme anaerobic metabolism from like being on a fan bike or sprinting all out, or under pathologic conditions like septic shock or really any kind of shock or hypoxic respiratory failure, et cetera, then it can go up to greater than 500 to 1 lactate to pyruvate. That is a huge amount of range. These changes during exercise and other stress strain response dwarf other metabolic signals in magnitude and span. Hence, lactate dynamics have a rapid and major short and long-term effects on cell redox and other control systems by inhibiting lipolysis or fat breakdown in adipose via this HCAR1, the muscle fatty acid oxidation uptake via this malonyl-CoA and CPT1, carnitine-palmitoyltransferase 1. Lactate controls energy substrate partitioning. Repeated lactate exposure from regular exercise results in major effects at the level of expression of regulatory enzymes of glycolysis and mitochondrial respiration. Lactate is a fulcrum of metabolic regulation in vivo. So pretty interesting findings about lactate and kind of like new discoveries about lactic acid compared to what was previously understood. It says in this paper, aerobic glycolysis and lactate production and oxidation, notwithstanding the Warburg effect of aerobic glycolysis in cancer. Next video. Vita Infra. We now have good support showing that aerobic glycolysis leading to lactate production occurs continuously in resting humans as well as during stressful conditions such as exercise, high altitude exposure, trauma, pancreatitis, sepsis, myocardial infarction, and heart failure. At the outset of this discussion, it is important to note that lactate is an inexorable product of aerobic glycolysis. Important and regrettably, there are no solid experimental support for the traditional view that glycolytic flux is directed to mitochondrial respiration solely through pyruvate uptake by the mitochondria. In the past, it was assumed by many that the rising lactate abundance in the body indicated anaerobic conditions at the level of the cell, but our understanding of lactate as a metabolically valuable carbohydrate has now replaced this traditional view. I'm going to push back on the author a little bit because what is this author actually saying? He's saying that it's produced continuously at rest at a small amount, 10 to 1 of lactate to pyruvate, right? But then he gives examples. And this is where I have to be a doctor, right? So what happens with high altitude exposure, low oxygen? What happens with trauma, hemorrhagic shock, and, ischemia, lack of perfusion to tissues, pancreatitis, most cases are very benign and probably not going to have a significant lactic acidosis. But if it's severe and it's like a necrotic pancreatitis or some kind of like septic pancreatitis, then it just goes back to perfusion, oxygenation, myocardial infarction. What is that? Lack of blood getting to the heart muscle, therefore lactate production, no oxygen, no blood, heart failure. So my point is that he's saying that our understanding is way off about how lactate is viewed, but he gives examples of how lactate has kind of always been viewed. So I think that he wants to make kind of a big stink about how lactate is so much more differently viewed now. And I think it really, what I can understand from both of these papers, because he's an author on this paper as well, is that they want to say that this aerobic glycolysis, basically lactate being produced at normal conditions, is a thing. It's not only black or white, anaerobic or aerobic. So I think that's really what the discovery is, in my understanding. It's just that when oxygen or blood flow is limited under things that we already knew that was going to lead to a lactic acidosis, then he shows that it does, right? So basically what it says here is that, nominal muscle lactate concentrations range from 0.5 to 1 millimole at rest. And then the dynamic range can be 20 to 30 fold higher, going from 10 to greater than 500 millimoles, or from 10 to greater than 500 lactate to pyruvate ratios. And basically, it's just going to be less of a black and white. It ranges from very low to very high, depending on how much oxygen and or blood is getting to those tissues. So what are we looking at here? We've got a lot of texts, but it really, what are they at the end of the day saying? What they're saying is that under normal physiologic conditions, there is some degree of lactate made, a very low amount, but that lactate can be recycled to be brought into mitochondria and fully oxidized by oxidative metabolism with healthy mitochondria intact. And of course, if oxygen is present. So that is going to vary widely. So it's going to go from, pyruvate being 1 and lactate being 10 under like at rest, but under duress or under stress or under hypoxia or low oxygen or lack of blood flow, ischemia, then that ratio can change rapidly to go from 10 to 1 to 500 plus to 1. And some of that lactate is going to get broken down by local mitochondria in the actual cell that it's being produced in, or in other cells surrounding it that actually have better blood flow. And it also kind of like talks a little bit about how there's 3 major mechanisms. And one of the major mechanisms that was not really talked about with a graphic much from the paper was the Cori cycle. And that's where basically lactate is produced here by these muscle cells or by whatever cells that are not having enough oxygen or energy from oxidative phosphorylation. And that lactate is going to get brought back to the liver, and that is going to get reconverted back to pyruvate and back to glucose. This is gluconeogenesis using lactate as the precursor. And that is an energy dependent process. And this is kind of the classical way that we believe that the majority of the lactate was being reconverted. That also seems to be like part of the kind of newer discovery, is that at rest, 50% of the lactate is being converted by this Cori cycle, and the 50% is being converted by the other cells. And then during exercise, then the Cori cycle is going to be contributing 75 to 80% of that, which is why blood lactate levels are going to rise, because it probably supersaturates the ability for the local tissues to convert that lactate. And so that lactate is going to get back to the liver and through the bloodstream and be converted back to glucose through this Cori cycle. But I wanted to at least show that. And then lastly, for anybody who, wants to know a more exhaustive list of pathophysiologic conditions that can lead to a lactic acidosis. I pulled this from Up to Date, which is a resource we have. So these are kind of like disorders of increased pyruvate production. So here is enzymatic defects of gluconeogenesis or glycogenolysis, respiratory alkalosis, pheochromocytoma, beta agonists, or drugs that work on beta receptors, impaired pyruvate utilization, there's congenital reasons, and then there's altered redox states such as enhanced metabolic rate, grand mal seizures, severe exercise, hypothermic shivering, severe asthma, probably due to hypoxia, I'm guessing, and then decreased oxygen delivery. This is probably the majority of places we see this in medicine. So in any kind of shock, whether it be septic, hemorrhagic, any kind of shock situation, cardiac arrest, which is kind of like a very similar shock, pulmonary edema, carbon monoxide, severe hypoxia, those are all related to oxygen delivery. And then, so basically what I'm trying to get at is that this author is trying to make it seem like this is completely different than before. I don't think so. I still think we have a lot of black and white. Like, here's all the issues, like on this list, right? This is this list on this red, and this is kind of like at rest. What this author and other authors are basically saying is there's more of a gray area with lactate. It's not black or white, aerobic or anaerobic. It's just that the amount of lactate produced at rest is very low, but it can be very high very quickly. And that's what makes this anaerobic metabolism the backup generator when oxygen is low or when demand is very high. And I hope that made sense. And I hope this will also make the next video about aerobic glycolysis and the Warburg effect make much more sense. If you like videos like this, please like, share, and subscribe. And until next time.